Math 1314, Tyler Junior College, Section 1.6, Other Types of Equations. In the previous videos, we've discussed polynomial equations, which we solved by factoring. We discussed square root equations, which we solved by squaring at the right time, but we also had to check our solutions. And most recently, we've solved quadratic-like equations, which are equations that were not technically quadratic, but under the right circumstances and with a good substitution, transform them to quadratic equations, at which point we solved them, put the substitution back in, and then proceeded to finish solving the original equation. In this type of equation, we're going to have exponents that are rational numbers, hence the name rational exponent equations. For example, we're going to solve x to the 2/3 power equals 64. And we're also going to solve x to the 3/2 power equals 64. But how do we solve either? And what the heck do these rational exponents even mean? I mean, I know what it means to square something. If it said x squared, I know what that means. That means x times x. Or if it said x to the 3rd power, I know what that means. That means x times x times x. But how do you raise something to a 2/3 power? Or a 3/2 power? Or any other rational exponent that's not an integer? Well, the answer lies in an exponent rule. How to raise something to a rational exponent power. It's pretty straightforward. This is technically considered review. So, if you raise something to a fraction power, we'll say x to the m over n power. The numerator of the exponent does represent a power, but the denominator represents the index of a radical. In other words, you set up a root, and the denominator tells you which type of root to take. 2 would be square root, 3 would be cube root, 4 would be 4th root, etc., etc. Now, you can write this two different ways. You can either say the nth root of x to the m power, or you can say the nth root of x altogether raised to the mth power. In other words, it doesn't matter if you do the index first as a radical, or if you do the power first as an exponent. As long as you correctly assign the numerator of the rational exponent as an exponent, but the denominator of the rational exponent as the index of a radical, it will be set up properly. So just a quick example numerically, and then we'll get back to solving these equations. For example, let's say I asked you, what is 125 to the 2/3 power? We can write this one of two ways. We can say the cube root of 125 to the 2nd power, 2 being the numerator is the exponent, 3 being the denominator is the index of the radical, or we can say the cube root of 125 first and then raise to the 2nd power. Both of them will give you the same result. Which one is easier? Honestly, it depends on the technology that you have. But in practice, it's actually easier to do the index first. Doing a radical on a number typically makes it smaller. A power typically makes it larger. So our options are make the 125 really large and then find its cube root, or take the cube root of 125, make it small, and square that answer. I'm going to go with the cube root first. Now, what does it mean to take the cube root of 125? Well, to take the square root means to find the number that you multiplied by itself twice to get the radicand. To find the cube root means what number do you multiply by itself 3 times to get the radicand. Radicand being the part under the radical. This is equivalent to saying, what do I raise to the 3rd power to get 125? Now, you may have to guess, or you may have a calculator that can do it for you, but 5 to the 3rd power is 125. And what that means is the cube root of 125 is 5, but we haven't squared yet. And 5 squared, of course, is 25. So that means that 125 to the 2/3 power is 25. Would we have gotten the same answer if we had squared the 125 first? Yes. If you square 125, you'll get 15,625. And now you have to find the number that multiplies 3 times in a row to get 15,625. With the calculator, it's a moot point which one you do first. If you're doing it manually, I would recommend doing the radical first. So let's get back to the rational exponent equations, starting with x to the 2/3 power is equal to 64. Well, how can we solve this? Well, the answer is in one move. That one move would be to raise both sides of the, well, let's think about this. We want to get the x by itself, right? So we need to do something to both sides that will get the x by itself. So what can we do to make this 2/3 exponent disappear? Well, we have a rule that says when you raise a power to a power, you multiply them. So I'm thinking that I want to raise both sides to a power, but what power do I want to raise it to? If my objective is to get x by itself, then I would like that power to be 1. So here's what I'm thinking. I need a number that I can raise both sides as a power to, but on the left side, when they multiply, give me 1. So what can you multiply by 2/3 to get 1? Answer, it's reciprocal. If we raise both sides to the reciprocal power, which in this case is 3/2, that will set up a multiplication problem in the two exponents that will give us a product of 1. So the step here is to raise both sides to the reciprocal power. We'll bring this problem back in just a minute. So, x is 64 to the 3/2 power. But what does that equal? Well, according to our rule, the denominator, 2, means that we would take a square root. In a square root, the implied index is 2. It's rarely written, but I'm going to write it for emphasis here to emphasize that the denominator dictates the index in the radical. And the numerator, 3, represents a power. And we can put it on the 64 or we can put it afterwards. I choose to put it afterwards. So what's the square root of 64? 8. We haven't done a 3rd power yet. And what's 8 to the 3rd power? 512. We can check by raising 512 to the 2/3 power. That would be asking for the cube root of 512 raised to the 2nd power. And you may not know the cube root of 512. I do, because I know what number I multiplied 3 times in a row to get 512. That number multiplied 3 times in a row gives 512. So the cube root of 512 is 8, but that's still getting squared. 8 squared is 64, and we're good. So far. There's always got to be a so far. So why did I say so far? Well, what if I told you there was a second answer to this equation? Because there's a second number that we can square and get 64. What else can we square to get 64 besides 8? Negative 8. But now that raises the question, can negative 8 be the answer to the cube root of something? Yes. Because what do you get when you multiply negative 8 3 times in a row? When you multiply positive 8 3 times in a row, you get positive 512. But if you multiplied negative 8 3 times in a row, you would get negative 512. So is negative 512 also a solution? Well, is the cube root of negative 512 negative 8? I thought we can't have negatives under radicals. Oh, that's square roots. For cube roots, it's a different story. If you're going to claim that the cube root of negative 512 is negative 8, then you should be able to check it by raising negative 8 to the third power. I already know that 8 to the third power is 512, but what happens when you multiply 3 negatives? The first two multiply and become positive, but then the third one swoops back in and makes it negative again. So yes, negative 8 to the third power is negative 512. Which means the cube root of negative 512 is negative 8. Which means that negative 512, which would give us a negative 8 here, which squares into 64, is a solution to this. So it's like we picked up a plus minus. But where'd that come from? Why did this guy pick up a plus minus? The answer is super stealthy, but predictable. We've seen the insert a plus minus move previously when we were solving quadratic equations. It went something like this. If you have an equation and you square root both sides, put a plus minus in it. Where did we square root both sides of an equation here? Where did we do anything to both sides of the equation? Here. But what does this 2 in the denominator mean to do? Square root. So when we raise both sides to the reciprocal power, because the reciprocal had a 2 in the denominator, and more generically an even number in the denominator, that set up the exact situation that invokes a plus minus. Okay, I'm saying a lot of words and referring to a lot of old stuff, but what does this mean that you have to know? The following. If the original rational exponent so this one has an even numerator, use a plus minus when raising both sides to the reciprocal power. I know it's a lot of words to say use a plus minus now, but if your rational exponent on the variable has an even number in the numerator, then raising both sides to a reciprocal power will take an even root, which is what brings the plus minus. I know this raises the question, what if it's an odd numerator? Well, didn't we have an example that I raised a minute ago that did? Yes, but because we were already at the 13.5-minute mark, we're going to do the next example, x to the 3/2 power equals 64, in the next video.